10.2, we're going to work more with probability, and we're going to look at how to count the outcomes that we can get best, and how to use something called a tree diagram to help us with that. So in the first example here, we have boxes of cereal that contain toys, and they're equally distributed, and Talia wants to collect a complete set of the different toys. And in part A here, it says there are two different toys. What is the probability she will find both of them in her first two boxes? When we open the first box, there are two things that could happen. We could either get toy A or we could get toy B. And then if we got toy A and we open a second box, there are two things that could happen then. And the two things that could happen is we could get toy A or toy B. And similarly, if we got toy B on the first box, opening the second one, we could either get A or we could get B. We can follow the branches of this tree to write down the different outcomes that could happen from these two events together. We could get toy A and toy A, or we could get toy A and toy B, or we could get toy B and toy A, or we could get toy B and toy B. So by listing out these outcomes, we can look at them and see that we have four possible things that could happen, and two of them satisfy what we're looking at, getting both of the toys. So this probability is equal to 1/2. In the next part, we expand this to having 3 toys, and we want to know what the probability is that we get all of them after opening 3 boxes. So on our first opening, there are 3 things that could happen. We could get toy A, B, or C. And then from each one of those, there are 3 outcomes. And we can label them A's, B's, and C's. Toy A, toy B, or toy C. And then after each one of those, there's a third box opening, and there are 3 outcomes that we could get from that. We could get toy A, B, or C. So here's the completed tree diagram. And we could list out every possible combination, but we can see at the end here that there are 27 outcomes that we could arrive at. And then I can run through these branches to see which ones meet the criteria of getting all 3 toys. So I could get an A on the first one, and then a B, and then a C. Or I could get an A on the first one, and then get a C, and then toy B. So there's 2 successes so far. Or I could get a B, and then A, and then C. Or I could get B, C, and then A. There's 4 things that work. And then I could also get a C, A, B, or a C, B, A. So that is leaving me with 6 successes out of 27 paths possible, and that reduces to 2/9 as our probability of getting all 3 toys in 3 boxes. Now let's take a look at the investigation. And step 1 says to look at example A, part A. This was our tree diagram, calling them toy 1 and toy 2 as opposed to A and B. But when we open that box, the probability of getting toy 1 is 1/2, as is the probability of getting toy 2. When we open the second box, we have two things that could happen. We could get toy 1 or toy 2. The probability there is 1/2 that we get each of them. And so we're getting toy 1, toy 1, toy 1, toy 2, toy 2, toy 1, toy 2, toy 2. And these are 4 possible outcomes. The probability of getting each of these is 1/4. And then what we did in the example is we added those two things together. Step 2 in this investigation tells us to redraw the tree diagram for example A, part B, and indicate the probability on each branch and also write the probability of each path. So if I go back to the tree diagram that I made here, when I open the first box, it's 1/3 for getting each toy as its probability. And when I open the second box, the probability is 1/3. When I open the third one, the probability is 1/3. And every branch on here would be labeled as 1/3 for the probability. Because the probability of getting any given toy out of any given box is always 1/3. And so if I record the probabilities like it asked me to, 27 possible paths, A, then A, then A would be 1/27th. A, then B would be 1/27th. A, then C would be 1/27th. And each path has a probability of getting what we want, getting that path 1 out of 27 times, the probability. And it says, what is the sum of the probabilities of all possible paths? Well, that sum is 1, because one of those paths will always have to happen. And if we look at the paths that are highlighted, 1/27 plus 1/27 plus 1/27, 1/27, 1/27, 1/27. That's 6 1/27s being added together, or 6/27ths, like we got in the example. Step 3 asks you to look at 4 different toys now. And it says to only draw enough tree diagram to answer the questions that you have to answer. And you might have noticed in the previous tree, it got pretty big pretty quick and hard to fit everything on. So why don't you go ahead and start drawing this, and I'll draw part of it too. So here's a part of this tree diagram. And the path that I drew out is getting the first toy, then the fourth toy, then the first toy, and then we could pick any other one here. So if we do this, if we were able to fit the whole thing on the page, you drew a very small one first off, but what we would end up with is 4 times 4 times 4 different paths that we can get. So I'm going to look at the questions I need now and see if this is sufficient. So what would be the probability of getting toy 2 in the first box? Well, that's going to be 1/4. What's the probability of getting toy 2 in the second box? Well, it's still 1/4. And in any box that we open, the probability of getting any particular toy will be 1/4. And in these situations, it asks, does the toy she finds influence the probability of there being a particular toy in the next box? No. No matter what box we open when, we'll always have a 1 out of 4 probability of getting any particular toy. Now it says one outcome is 3, then 2, then 4, then 1. What is the probability for this? So if we were to look at the tree, we could trace out this path going 3, 2, 4, 1. It's asking what's the probability of this. Well, there are 256 different paths if we were to count them all out in that tree. And one of them matches this exact path. And then if we were to look through this and check the rest of the arrangements, what we would find out is that there are 24 paths that contain 3, 2, 4, and 1. And they are all equally likely. So that takes us to the next question. Write a statement explaining how to use the probabilities of a path's branches to find the probability of the path. Well, you count them. You count the number of paths there are, and you add up that many probabilities. So in this case, it was 1 over 256 to get that, the one in step number 3, or step 2, right here, 3, 2, 4, 1. And then we have to add 24 of those together. In other words, do this times 24. And then this is reducible. We can take 24 and chop it in half. 256 chopped in half is 128. Chop this in half again, we get 6 over 64, or 3 out of 32 as our probability. Now, one thing I'll point out with this, I'm going to go way back to the beginning. This tree diagram right here, one branch was 1 over 27. One way we can get that by looking at the tree, instead of counting up all of them, we can do 1/3 times 1/3 times 1/3 is 1/27. And if we look at the tree that we filled in, here, 1/2 times 1/2 is 1/4. And that leads us to the multiplication rule for independent events. Those opening of boxes, because the probability remain constant, those events are independent. And if we have the probability of something and something else and something else and so on, and tells us to multiply those probabilities. Probability of the first thing times the probability of the second times the probability of the third. So and means multiply. Now we're going to draw 3 cards, one after another, from a standard deck. Standard deck has 52 cards total. And in that deck there are 4 suits, and each suit contains 3 cards. So I want to know what the probability is that I will draw exactly 2 hearts, and what that means is that I want 2 hearts and one of something that is not a heart. So there are 13 hearts out of 52. That's the probability of picking a heart. Times. Now this doesn't say anything about putting the cards back again. So that means that now there are 51 cards in the deck. And there are only 12 hearts left. So the probability of getting a heart on the second draw is 12 out of 51. Times, time to pick the third card. Now there's only 50 cards left. And of those 50 cards, we knew that we started with 13 hearts. That means that 39 cards are something other than a heart, a spade, a club, and a diamond. So this last one is 39 over 50. But now we have to count up the number of ways that this can happen. We could get a heart, and then any one of those other suits. So that's 3 ways. Or we could get a heart, any one of those 3 other suits, and another heart on the third pick. That's 3 more ways. Or we could get any one of those 3 suits, a heart, and a heart on the last 2 cards. That's another 3 ways, for a total of 9 ways to get a heart, and something else. So I have to take this probability, this one branch of the tree that satisfies my conditions, and multiply it by 9 to get the total probability. And if you're plugging it into your calculator, I would really recommend that you do each fraction in parentheses just to avoid any mistakes. And what we've just done is something called conditional probability. We're taking the probability of dependent events, because once I picked the first card, that changed the makeup. It changed the probability of getting a heart. So this quantity right here, this 12 over 51, that is the probability of getting a heart given that I already picked a heart. So knowing that I already picked a heart, that means that there's only 51 cards left in the deck. And of those 51 cards, 12 of them are hearts. So dependent events, the probabilities change from pick to pick. And we're going to look at the difference here between dependent and independent probabilities. So we're going to find the probability of getting a face card and then not a face card. And part A deals with replacing the first card. So in a deck there are 12 face cards out of 52 times, now I'm putting the card back into the deck again, so there are still 52 cards to draw from. And I want the other card to not be a face card. I got this backwards. The first one, it says, needs to be not a face card. So the ones that aren't face cards, 12 of them are faces. That means 40 of them are not. And there are 12 faces, and we would just multiply this together. Part B says we are not replacing them. So we would do 40 out of 52. There are 40 non-face cards out of 52. But now on this pick, there's only 51 cards left in the deck. And 12 of those 51 are face cards. And so we just have to multiply these together to give us our probabilities. Here's the 10-2 assignment.